It took about a month before I hit my first aha, and then after that I've loved it ever since. So I'm going to start by doing a quick Envy refresher, look at some of the problems with Envy, the solution, at least from our team's point of view. Going to touch quickly on Black Knight, and then going to talk about how we map Envy to Eclipse, and that'll discuss our system architecture. So Envy was a product built by OTI. It was both an IDE and a version control system. It formed the basis of IBM's Visual Age Smalltalk, and provided a central database so that every time you hit save, your changes went to the database. This was very safe, but it had some serious problems if you're trying to work on a wide area network. So Envy provided version control, and this is where I guess we hit Gilad's modularity from yesterday, because it provided code organization structure. So you grouped your classes into applications, and your applications also had a class. And all your applications can be grouped into tree-like structures. So you had sub-applications underneath. These are usually used to tailor your code for platform-specific things, i.e. your file systems, Unix versus Windows. So like normal Smalltalk, all your classes contain methods. And version control is all done at the level of these methods. And Envy also allows you to have class extensions, so you can extend applications from other applications. And once you've got a number of these applications together, you want some way to group them into groups of functionality so you can make members. So there are a number of other goodies that you get when you deal with applications. And one of these is prerequisites. This is one way you can say that this application requires the following applications, so that you have proper scoping. You're not trying to reach into applications that aren't necessarily going to be loaded. You also get lifecycle events. So when your image shuts down and your image starts up and your application gets loaded, it provides a lot of nice hooks for you to deal with anything you need and properly handle things. You also get a lot of rich metadata. So you can ask your application what classes it defines, who extends it. There's a lot of really neat things you can do, but it really ties into that Envy version control system. So we have a lot of problems with it. You really have to be on a local area network, otherwise it's almost undoable. In fact, for our team, when we were working with research teams, we ended up just using extra boxes on our network that remote desktop into those so that they had a local connection in. It makes it hard to take your code on an airplane. You either have to create an island database and then sync your changes manually back and forth, or you lose your connection to your database, to your repository. There are a number of version control limitations as well. There's no way to make lightweight tags, for example, CDS tags. So it makes it really difficult to get back to last Friday's build unless you version all your configs, which is probably a little heavier maybe than you want. So one of the other problems is Envy has a very strong notion of user roles and what different users can do. So you have to become an owner of a class before you can release it. Only the library manager can do certain things. And it's really, there's no real analogy to this in most version control systems. And it's hard to get new grads up to speed on this. People get confused. Why can't I do this? I've done everything I should have done. And I'm told one of the first tools everybody hacks up is a very quick way to become another user. So for us, we also have problems with a disjoint tool set. So when we bring somebody on board, we say, look, here's your copy of Eclipse. You use that for all your C and C++ code. You use that for all your Java code. Oh, yeah, for your Smalltalk, you have to use Envy, which is really confusing for a lot of people. And it leads to visibility problems. When your C code and your Smalltalk code have to interact, it becomes easy to miss releasing part of your change. And for our team, at least, we have a significant investment in VM construction tools. And Smalltalk's a great language for doing this kind of stuff. You get to play all kinds of neat tricks with reflection it does not understand. And there's just, I don't know what other language you'd use to be able to do this as nicely as you can with Smalltalk. But we have a lot of dependencies on Envy metadata with this, and our tools work well. They're very likely to change. So the solution, at least for our team, is we want to keep the Smalltalk language. We don't want to change our valuable tools. But we do want to put everything under one roof. We want to have a single file-based source control, currently CDS. And we want to have the Eclipse IDE handle all the languages we work with. And we want to get rid of the concepts that confuse people, like become another user. And we want to get rid of the MV database in the background, because that's what ties us to a global area now. So this is probably sounding familiar to a lot of people. John O'Keefe and John Dumovich were doing a project a number of years ago called Black Knight. It was a very ambitious project. They wanted to replace the class libraries, the UI, and the runtime model. They were going to have .binary files for compiled Smalltalk, similar to Java's .class files. Well, it's a hard problem, and we haven't been able to get that ambitious. What we're looking to do is we're going to replace the UI on NV. We're going to remove the connection to the library, but we're going to keep the class image mode. So we've jokingly been referred to as the gray squire. So how do you map these NV concepts to Eclipse? Well, let's start with our config maps browser there. Each of our configuration maps becomes an Eclipse project. And this imposes certain limitations on your config maps. And in NV, you have no problem having an application defining multiple config maps. In our world, we say no. You get your application only be defined with one config. So your configs also have the idea of required maps. And we've implemented that using Eclipse reference projects. The nice thing about this is Eclipse does all the hard work for us. It creates the necessary tree structure and will tell us if we have cycles in the dependency graph. And for dealing with config expressions, we've added .smalltalk files, which control the image builder, so it won't load things if it doesn't meet the config expression. So each of your applications becomes a project in Eclipse. Becomes a directory underneath one of your projects. And these applications also get their class, and that class still gets lifecycle events. We've kept the tree structure, sub-applications become subdirectories. Every class becomes a .st file, and every subclass becomes a .stx file. So
repeat that last one.
Every class becomes a .st file, so we have our own file format, and every extension becomes a .stx file. So now that we've run through quickly what our problems and solutions are, I'm going to go over our system architecture. So I guess I should probably start by describing why you're seeing the word graph there. We were trying to come up with the internal name for this project. We had envy, so we thought let's look at the 7 deadly sins. And we like the idea of using lust because it has the ST in it. But my wife just wouldn't appreciate me coming home saying I woke up lust all day. So we opted for wrath. So starting on the left side of that diagram, we have our headless image. And in that image, we have our wrath application, which allows us to control the image. It's basically our entry. So it sits and reads off a queue of incoming packets, processes them, and sends the results back. So our wrath.exe is our launcher application. It starts up and waits for a connection. Once it gets a connection, it launches the image. All of the socket level code and transport level code is handled in that launcher. So it's got a loop that reads off the socket and fills the incoming request queue, and a loop that sits on the outgoing request queue and sends everything off to the socket. It's all done with platform functions, which was a bit of an interesting thing to learn. So all of the actual conversions of these packets into usable commands are done in the Smalltalk image. So on the other side of our line, we have our Eclipse side, which is a dual mode design. A lot of people in our team, when they're working, won't be making changes in Smalltalk code, so they don't want to eat the cost of running a Smalltalk image and having it, fill up Eclipse's memory because Eclipse is large enough as it is. So we have the disconnected mode, which lets you edit Smalltalk code and browse Smalltalk code, but you don't have to have the image running. But it means you can't evaluate anything, you can't execute anything. So that when you connect, you get your Smalltalk debug and your connected UI, and you get to do things like browsing linkers, senders, and messages. So it becomes a much more powerful system. It becomes much closer to a real the other thing we have is we have an extra socket from the image to the connected UI that provides the transcript. So the first phase for our project was file-based Smalltalk. This is where we made a meta model to map classes and methods to their files. So we have things like FB application, FB sub application, all the way down to FB method. This allows us to keep the source on disk rather than trying to load it into the image. We looked at one point at moving all of the source into the image in the way that do it store your source, but that the image ballooned to a gigantic size too quickly. So we opted for this model instead. So we have an FB loader, which given a file, will create our meta model objects and pass them over to the FB resolver, which you can think of as the Smalltalk dictionary for our file-based Smalltalk. We modified the image builder to be able to load this stuff. And at this point, we had proved that this was possible for our environment. So we could go to management and tell them, there's no more risk of changing text editors. So here's an example of our file format. On the side, you're seeing the file for the .st file for compile method. Extensions use almost an identical file format. They just have less metadata at the top of the file. We don't allow extensions to add instance variables. It's possible from a file format point of view, but I have to go hack it into the image builder, and I'm not entirely sure how long that would take me. So the nice thing about this format, though, is it's very simple. It's line-based. You don't have to understand Smalltalk to be able to parse it. You can skip over the Smalltalk parts. And it's enough for us to get the Eclipse views out and running. And yes, it's ugly. We've looked at a couple of other formats, but parsing level, you end up doing too much extra parsing, there's too many special cases, so we figured this was enough to get us up and running. So, I've talked a lot about the image builder, and this is what's responsible in MB for loading classes. What it does is it uses EM builder class and EM builder application, etc., to build up a parallel hierarchy of what you're going to load. Once it has this parallel hierarchy, and it's sure it's going to work, it morphs it in and makes all these classes live. So it's atomic though, so we either all go home or no one goes home. So from Eclipse, it tells us that a file's changed. So we convert our file into our meta model objects, and then we had to get a way to hook these into the EM builder hierarchy and get the image to load them so we can connect them to all the live classes. This has been a fun piece of code to work on, because once you break the image builder, you're done. It's time to go get a new image and start over. So, NV allows you to reload things at the method level, and Eclipse deals with things at the file level. So you have quite a bit of impedance mismatch there. So if we're looking at this method, how do we determine that it's changed? Well, we looked at the compiled method and said, well, it's got 4 instance variables and 3 slots, the last one being a magic one used by the library, so it can point back to where the source came from and to store some status bits. So we said, well, the easy thing to do is just add some instance variables. So we figured we'd add a timestamp and a CRC of the source code. Well, the VM knows the shape of the compiled method. So any attempt to add instance variables causes you some interesting behavior. Either your method won't run, or we added transcript show commands to the methods to ensure they were running. And they do run that, but not completely, and they always return nil. So we said, you know, well, I guess we have to steal slots just like everybody else. The problem is with the compiled method, everybody steals slots. DBG breakpointing method steals slots as well. One to point back to the original method, and one to hold the breakpointing for, which provides you the necessary information to know what the original bytecode at that PC was. So if we want to steal slots, we have to be careful about where we do it and how we do it. So we figured let's steal the second last slot, because for the time being I still have to exist with a running library until I've killed the connection. So what we did is we stole the second last slot so we can leave a file pointer alone. So when Eclipse So to deal with DBG breakpointed methods, we decided that the best thing to do was simply to add our extensions to that class and have them always forward our messages to the original method. And that way we had we didn't have to worry about stepping on their swollen slots or them stepping on ours. So if we get a file notification from Eclipse that the file's changed, we then want to determine which methods in that file have changed. So we start building up our meta objects, and we go through and we say, well, the timestamp on this has changed, so we check the CRC of the source. If the CRCs match, we don't want to reload the method. So what we end up doing is we just hammer the new timestamp into the old method and continue along without reloading. So at this point, we've had our file-based Smalltalk running on one side. So now we want to get our Eclipse browsers up there. So we want the same basic functionality you get in a We want an applications hierarchy and a hierarchy browser. And we want to hide the file format so you only see things one method at a time. At this point, you can edit code, but none of the changes are reflected in the image. You have to do a full reload. We haven't quite got the synchronization working properly. And we create an index of all your Smalltalk files. So we basically have a Smalltalk dictionary in Eclipse that'll map back and forth the class that was formed. We also have problem markers for all file format problems. So if you've messed up your file format, we don't yet have problem markers for compiler errors, but we're working on that next. So I can show you screenshots of these, but screenshots just aren't much fun. So let me pull up the actual browser. And of course, it won't show on the right screen. So it's very strange for this. So here's our applications browser. So we're looking at compile method. We can see both its instance methods and its class methods. You can filter them so you only see the public methods or only see the private methods. You can see just a method at a time. Unfortunately, or as is normal, you're only seeing the methods defined in this application. So if we said we wanted to see compile method and all of the extensions to it, we'd hit F4 and we jump across to the hierarchy browser. At this point, you can see all the subclasses of it, you can see all the superclasses of it, you can see what applications it's defined in, you can see what methods have been added here. The only thing is to open the Eclipse, unfortunately, has to open the actual file backing it. It can't just nicely slide it in the background. It's slow right now because I'm running a debug version of Eclipse, so I'm paying a fair bit of penalty for that. So I'll hop back to the presentation right now. So those are our browsers. And at this point, we said, okay, it's time to connect the two sides. So we thought about what protocol to use. We looked at XML, but XML has so much duplicated data in it that you don't really want to be sending that across the socket. So we came up with a very simple binary protocol. And the reason we did this was most of the protocols we looked at, for example, DGBP, which is used by languages like Ruby and I believe PHP. Everything you do in Smalltalk becomes pretty much an extension of their protocol. So at that point, why bother using the protocol? So we built our C transport layer, and it's a custom launcher. It starts up, and it doesn't start the image until it gets the first connection on the socket. And all the sockets are handled in C to prevent problems when reloading. And this was an interesting problem for us because for quite a while we weren't reloading the base image, we were just reloading classes and everything worked well. We had it all implemented in Smalltalk, which is what we wanted, and life was good. Until we started to reload base classes. And some of the loaded behavior of these classes isn't quite what you want. The SCI socket manager wipes all socket connections when it reloads. So if suddenly your control channel disappears, you're in a bit of trouble. So we found a hack around that. So the next thing that hit us was ES asynchronous calling, which is used anytime you want to do blocking socket calls in the image without blocking the whole image. When it reloads, it gives back all its memory for any of the future calls back to the OS. So we started to GPF in odd places. So we ended up pushing this all down into C. And that way we never spend any time locked in C. And that way we can reload the base image without having any problems. One of the other things we had to do with this to get it to work is the C launcher needs to be able to tell the image to shut down, which meant we had to figure out how to do user primitives as well, so we can pass back out to both system and primitive exit, so we can use the ES post async message to get that to shut down. So the other thing we did is we did transcript implementation. And what we did for this is we basically have a socket listener in Eclipse. And we let this socket exist in the image, and it just spits across memory before you want to send to your transcript. So it's easy to reconnect if your connection's lost, so we don't care if there's any problems when you're reloading this. The other problem we had with the transcript was, at least in our code, a lot of people know that it's a shell that's always going to be there. So if you're going to exec a long hop, it makes sense to just use the transcript. So we ended up just overriding that method and sending value to the log. So at this point, we had everything we needed to get a read-only debugger going. This took quite a while. The Eclipse tutorials on setting this stuff up are kind of out of date, and it's not the easiest thing to get fixed and get right. It's one of those wonderful chicken and egg problems. You need this to get that, and to get that, you need this, so you end up having to implement almost the whole thing before you have anything usable. So we wanted to make sure that we preserved proper Smalltalk semantics, things like selecting the correct stack frame on the long pattern. Interestingly enough, there was no way to do this in Eclipse. I guess none of the other languages ever selected anything other than top of stack. So we wrote patches that got submitted and accepted. The other one we wanted to make sure we got right was statement-based highlighting. We didn't want to do Java's line-based highlighting, so we made sure that we transfer all the required debug information across. And I said it's read-only, but it's not quite. If you want to write the Smalltalk code, you can update variables, you can change values, you can still run methods. So at this point, you actually can do